Hey everybody, how's it going? Today we're going to talk about critical points, local maxes and mins, and the first and second derivative test. I want to start with question 9, I believe, or excuse me, not question 9, question 29 in the Early Calculus Transcendentals textbook, which gives us 4 plus 1/3 x minus 1/2 x squared, and it asks us to find the critical points of this function. So finding critical points means that we are looking for the x values, or p values, or t values, or z values, depending on what variable they're using, where the first derivative of this is equal to 0. That is what a critical point is. So what we're going to do is we're going to take the first derivative of this, which is going to be 1/3 minus x, just 1/3 minus x, sorry. Because this x squared comes forward, multiplies that out, and this x just cancels out. So we're given f prime of x equals 1/3 x. From there, we can say 1/3 minus x is equal to 0, and we can say that x is equal to 1/3. And we're done. That's the end of this first problem. Because this is the point at which f prime of x is equal to 0, is when x is equal to 1/3. So we could go a step further, and we could figure out whether this is a local maximum or a local minimum by placing 1/3 here and evaluating a value before and after it. So if we plug in, let's say, negative 100 to this value, this place here will end up being positive, because what we get is 1/3 minus 100, which will equal 100 plus 1/3. And then we could put in a positive value, like plus 100, and we would just get 1/3 minus 100. So this becomes negative. So what this graph ends up looking like is the value is increasing, it's increasing, it's increasing, and then suddenly at 1/3 it starts decreasing, decreasing, decreasing. And that tells us that 1/3 is a local max, because it goes from positive to negative. If it went from negative to positive, it would look like this, and it would be a local minimum. Let's look now at question 31 from the textbook. And we will say we are given that 2x cubed minus 3x squared minus 36x is our f of x, which means that our f prime of x equals 6x squared minus 6x minus 36. Obviously, I have a common factor of 6's in here, so I can factor out the 6 to get x squared minus x minus 6. And then from here, we're going to try and factor this. We need something that multiplies to this and adds to this, which in this case is going to be 6 times x minus 3 times x plus 2. And from here we can find our critical points, which is going to be x minus 3 equals 0 and x plus 2 equals 0, which means we have a critical point at 3 and negative 2. And then we could do the same number line thing again here, but just to save time, I'm going to leave it up to your imagination. So 3 and negative 2 are two critical points here. Now that was another easy one. Now we go to something that's a bit more difficult at face value. We're going to go to 33, and we're going to see t to the 4th plus t cubed plus t squared plus 1. The first derivative of this is going to be f of x, or f prime of x equals 4t cubed plus 3t squared plus 2t. From this, we can factor out a t to give us t times 4t squared plus 3t plus 2. And immediately this looks like something that you can factor. When you actually go to factor it out and you get the 8 up here and the 3 up here, there is no number that multiplies to this and adds to this. So instead, we want to look at our handy dandy quadratic formula. B squared minus 4ac over 2a, which gives us negative 3 plus or minus the square root of 9 minus 4 times 4 times 2. And this ends up becoming a negative square root, which is it's not possible, right? Negative x ends up being impossible because you cannot have a negative square root, which means this right here is not factorable. So we can just determine our critical points from this value out here, and we can say that when this t is equal to 0, this entire thing will be equal to 0. So our one critical point this time round is t equals 0. Then we move on to question 35. I'm sorry if I'm going a bit too fast. I'm just trying not to dwell too much on the. We are given that g of y is equal to y minus 1 over y squared minus y plus 1. Now, when I first looked at this problem, my first thought was, well, hey, y minus 1 is a pretty typical factor for a polynomial, and this looks like a pretty typical polynomial. So you go to factor it, and you try y plus 1 times y minus 2, which isn't going to work, and you try y plus 2 times y minus 1, and that's not going to work either. So we can do the same thing and plug it back into the quadratic formula, or you can take my word when I say that this also does not factor. That's not important yet, but it will be important in a little bit. We can say g of y prime equals the derivative of the top, which is just 1, times the bottom, which is y squared minus y plus 1, minus the top, which is y minus 1, times the derivative of the bottom, which is 2y minus 1. And we're going to put that all over the bottom squared, which is y squared minus y plus 1 squared. This multiplies out, so we get y squared minus y plus 1 minus 2y squared minus 3y plus 1. And we put that all over the original, which is y squared minus y plus 1. And then we group terms up top here. So we can say negative y squared, because we combine this term and this term, plus 2y, because we combine this term and this term, and these ones cancel out. So we have negative y squared plus 2y all over y squared minus y plus 1 squared. And the way to find critical points when you're working with a fraction is to separate this into two separate equations and put them both to 0. So the first thing that we're going to do is we're going to say y squared minus y plus 1 equals 0, because this squared is irrelevant when finding critical points, because if there's a value in here that equals 0, it's going to equal 0 even if you multiply it by itself. So y squared minus y plus 1 equals 0. And the interesting thing here is we have already established that this does not factor. Once again, we can plug it into handy dandy minus b plus b squared minus 4ac over 2a, which gives us y plus minus y squared minus 4 times y squared times 1. We don't have any values for this, but we know that y squared times 4 is going to be greater than y squared. So they're going to divide out and give us another critical square, which is amazing. So there are no critical points to be 14. So now let's look at our other one. Negative y squared plus 2. And let me move it down here, just so that we aren't in the way of everything else. And we're going to set this equal to 0. And we're just going to solve. First thing we should do is we should factor out a negative y. It's going to give us negative y times y minus 2 equals 0. And that makes this super easy for us. We can say that this can equal 0, because if this y equals 0, then this whole thing will equal 0. So we have y equals 0 as one of our critical points. And we can say y minus 2 is equal to 0. So y equals 2 is another critical point of ours. Now, we can move on to our next question. Let me flip my review sheet over here. Over to question 36, which this is our last question in section 4.1. We are given p minus 1 over p squared plus 4. So we're just going to do quotient rule again. Derivative of the first, which is just of the derivative of the top, which is just 1, times the bottom, which is p squared plus 4, minus the top times the derivative of the bottom. And then let's just go ahead and simplify this real quick. We are given negative p squared plus 2p plus 4 when we multiply everything out here and add everything together. And that negative p squared plus 2p plus 4 is going to be divided by p squared plus 4 squared. Just like that. So let's start with the bottom this time, because we're going to do the same thing. We're going to set both of these equal to 0. P squared plus 4 equals 0, because remember, this square doesn't mean anything when we're looking for critical points on the bottom of the fraction. P squared plus 4, we can say p squared equals negative 4, and oh, this doesn't look good. P equals the square root plus minus the square root of negative 4. Again, we cannot have negatives inside of square roots, so there is no critical points to be found on this bottom here. Next, we'll look at negative p squared plus 2p plus 4. Negative p squared plus 2p plus 4. Now, for the first time, we're going to use our handy-dandy quadratic formula, and it is not going to come up as a negative square root. We are given negative b, which is just going to be negative 2, plus minus the square root of b squared, which is 4, minus 4 times a, which is negative 1, times c, which is 4, all over 2 times negative 1, so negative 2. Now we're going to want to simplify things down here a little bit. Negative 2 plus minus the square root of 4 minus 4 times negative 1, so plus 4 times 4. So 4 plus 16 gives us 20 divided by negative 2. Now, this looks to me like something that can simplify a little bit further. Let's simplify down the radical root 20, which I'm not sure how you were taught how to do simplifying radicals, but this is how I was taught how to do it. I'm sorry if this isn't a familiar method, but please, just bear with me a little bit here. You take the 20 and you divide it by the smallest possible prime number, which is 2. You set the 2 there, and then you give the result of that. So 20 divided by 2 is 10. And then you take that 10 and divide it by the smallest possible prime number, which is 2. And then that leaves you with 5. And then the 5 just leaves you with 5 and 1. So then you take any pairs, which in this case we have a 2, 2 2's, and you group them together. And then you leave whatever's left behind inside the radical. So root 20 is equal to 2 times the root of 5. If you have a better way of doing that, I implore you to use it. That's just how I was taught to use it. So we're given negative 2 plus minus the square root of, plus minus 2 times the square root of 5 over negative 2. And from there, we can just divide to positive 1, because these cancel out, plus or minus the square root of 5, because these 2's cancel out. So our critical points are, what was our original variable? Was it p? Cool, p. P equals 1 plus minus the square root of 5, and p equals 1 plus the square root of 5 and 1 minus the square root of 5. And that is our last question in section 4.1. I'm afraid I don't have time to do 3.4 right now, but we will cover 4.1 and all of 4.3. Or quite a few problems in 4.3. Next, we can move on to 4.3a, which is going to be some questions about maxes and mins and concave up and concave down. So we're going to start with 9c. That's the first question that I'm choosing to do here in this section. It's 9c, which gives us that x cubed minus 3x squared minus 9x plus 4 And we need to find when this is concave up and concave down, and the intervals at which it is those two things. So we are first going to have to take the first derivative, because whenever something asks us, hey, is this concave up or concave down, what it means is when is the first derivative positive, which would be concave up, and when is the first derivative negative, which would be concave down. So sorry, give me 1 second here. I have a secondary monitor up right now displaying the textbook that I'm doing these problems off of, and I'm just making sure that I'm at the right page. So here we go. Page 300 in the textbook is where you're going to find this, and we are starting with question 9C, which is, 9C. Find the intervals of concavity and the inflection points. So 9C is given to us as x cubed minus 3x squared minus 9x plus 4. So we're going to take the first derivative, which is going to be 3x squared minus 6x minus 9. But we're not done. We need to take the second derivative, because that's where we find concavity, which gives us 6x minus 6, which we can then factor to be 6x minus 6 equals 0, which means x equals 1. And so our critical point here, or our point of importance to determine concavity, is going to be at 1. Because this tells us when this x equals 1 tells us when we flip sides. So we are given 1 as our possible point of inflection, and we are going to say that we need to plug in a value that is less than 1 into this equation here. So if I plug in, let's say, 100 to this equation, we get 6 times 100 minus 6, which is going to be equal to a positive number. So this section here is going to be positive, and then we can say 6 times negative 100 minus 6 will end up being negative. So this section here is going to be negative, which means anything before 1 is concave down, and anything after 1 is going to be concave up. It's asked us as well to write our notation for that, so we can say CC, meaning concave, down from negative infinity to 1, and then CC, meaning concave again, up from 1 to infinity. That is the end of that question there, unless, of course, we want to figure out what the y value is of our inflection point here. We know that the x value is going to be 1, but we can go back and we can plug 1 into this equation here, which will give us 1 minus 9 plus 4, which is equal to negative 7. So we can say that our inflection point is at 1, negative 7. Now we can move on to question 11C, which asks us to do the exact same thing. 11C is given to us as x to the 4th minus 2x squared plus 3. We can take the derivative of that, and it gives us 4x cubed minus 4x. And then we take the derivative of that, which gives us 12x squared minus 4. From there, we set 12x squared minus 4 equal to 0, and that gives us 12x squared is equal to 4, which goes to x squared is equal to 4 over 12, which gives us that x is equal to the square root of 1 over 3, which is also equal to 1 over square root 3. So, or excuse me, specifically plus minus square root 3, because we're taking a square root. So once again, we can draw our number line, and we can plug in one value as 1 over negative root 3, and one value as 1 over root 3. And now we need to find a value that fits into this section, and this section. Now, because we know that 1 over root 3 is greater than 0, and we know that 1 over negative root 3 is less than 0, we can just plug in 0 as our value here. And then here we can plug in 1, and here we can plug in negative 1, because we know that these values are going to be less than or greater than, in this case, our two critical points here, or at least our points of inflection, rather. So now we are going to want to plug in 0 to our equation here, where we have 12 squared minus 4. So we say 12 times 0 minus 4 is equal to -4. So we get a negative number when we plug in anything from this value. So we can say that this section here is negative, which means that it is concave down. And then on this section here, we can plug in, let's say, 12 times -100 squared minus 4. That's going to be positive because this -100 here ends up squaring into a positive 10,000. So we get positive for any value less than 1 over -√3. And then it's also going to be positive on the other side, because if we say 12 times 100 squared, it equals the same value as this right here. So we get positive minus positive. So this is concave up, this is concave up, and this is concave down. So our interval ends up being CC up from -infinity to 1 over negative square root of 3, then a union of 1 over positive square root 3 to infinity, and then CC down from 1 over -√3 to 1 over √3. And then, if we want to find our exact points of inflection, we know that one x value is going to be 1 over -√3, and we know that our other x value is going to be 1 over √3. So now we can plug those values in to this original equation here, which is going to be x to the 4th minus 2x squared plus 3. X 2x squared plus 3. And then we plug in our values. X to the 4th, we're doing 1 over the cubed root to the 4th minus 2 times 1 over, excuse me, not the cubed root, the square root. What am I talking about? Plus 3. So this becomes 1 over √3 times √3 times √3 times √3, which equals 9, because these two equal 3 and these two equal 3, and that equals 9. So we have 1 over 9 minus 2 times 1 over 3, to get this all out of the way here, plus 3, which gives us 1/9 minus 2/3 plus 3, which, if you multiply this out, find your common denominators, that gives us 22 over 9. And it's going to be the same regardless of whether you use the negative here or the positive, because both of these are even exponents, which means the negatives will cancel out if they are even. So our two inflection points are -1 over √3, 22 over 9, and positive 1 over √3, 22 over 9. So that finishes up 11C, and we are going to move on to 27, or excuse me, not 27, question 82. This one is a bit of a doozy, and it's a little difficult to understand. So question 82 gives us a formula and asks us to find the condition to make that formula work a certain way. So I'm going to take a second to write out the entire question here. Suppose F and G are concave up on any element from -infinity to infinity. These should be parentheses, not brackets. Under what condition on F will the composite function h of x equals f of g of x be CC up? So the first thing that we need to figure out here is what exactly this is asking us. It's telling us, when is this function here, h of x, concave upwards? So what we're going to do first is we're going to find h double prime of x, and we're going to see when that's positive. So h double prime of x, it's a bit of a doozy. It's just taking chain rule and then taking the derivative of chain rule twice. But what that comes out to is f double prime of g of x times g prime of x squared plus f prime of g of x times g double prime of x. I know that seems a bit long, but the fortunate thing is on this quiz, the worst thing that we can be asked is just this question here, and I'm about to give you the answer to it. So you could really just write one sentence for this question if it comes up and get the right answer. So this right here is always positive because f double prime of g of x, we've established that f double prime is always going to be positive because f and g are always concave up. So f double prime is positive, and this has a square, the second term here, so this is the first term, this is the second term. This second term has a square, meaning that is also always going to be positive. So this is always positive. So now we need to figure out what to do to make sure that this second term is always positive. We know that g double prime of x is always going to be positive because we are given that g is always concave up. So we need to figure out what makes f prime of g of x concave up. And I can tell you, the answer is that g prime of x needs to be, or excuse me, we need to prove that this is we need to say what's going to make sure that this is always positive. And that's going to be, it's always going to be positive when g prime of x is greater than 0. So f prime of g of x is positive when g prime of x is greater than 0. Because both functions are increasing, because f prime is given to us to be increasing, but it is not necessarily given to us to always be positive. So we need this inside value to be positive in order for us to have this function be increasing. I know it's a bit convoluted, it's very difficult to explain, but this is your answer to that question. G prime of x must always be greater than 0 in order for this statement here to be true. I'm sorry that I can't go more in depth with that. Finally, a little bit easier question for the first half of 4.3. We have question 88, which asks us f of x is equal to x to the fourth, and we need to show that f double prime of 0 is equal to 0, and that the point 0, 0 is not an inflection point. So this isn't too bad. All we have to do is say that f prime of x is equal to 4x cubed, double prime of x is equal to 12x squared, and then we can say f double prime of 0 equals 12 times 0 squared, which equals 0. Already we're done with the first half of that problem. Now we know that the x value of our point here, our potential inflection point, is 0. And if we plug that into our original formula here, we're given 0 again. So we have a possible inflection point at 0, 0. So now let's draw a number line, mark a spot at 0. And let's say the number we're going to use for this side is 100 and this side is negative 100. We come over to this function right here and we say 12 times negative 100 squared. Oh, well, that's positive because the squared turns to negative 100 times 100 into positive 10,000. Then we can say 12 times 100 squared is also positive because those are just positive times a positive. So we get positive, positive, which means that 0 is not an inflection point because it stays positive. It does not switch from being concave up to concave down or the other way around. That is the last question that we have on 4.3a. Now on 4.3b. I don't know what order I'm doing this in. I think that was 4.3a, which is on page 300. And 4.3b is on the same pages, but with different kinds of questions. So all of these questions I've been doing for 4.3 have been on page 300. Now we're going to look at 4.3b, and we are going to start with question 5, which, if I remember correctly, is very, very easy. So this question right here, we are going to be looking at a certain graph. So let me find the graph that we're going to be using. question 5. Here it is. Let me drag this over here. We are going to be using this graph right here. It asks us, given this graph, at what values of x does f have a local maxima or a local minimum? Now, this question is trying to trick you here because it's giving you the graph of f prime of x, which means that all we need to see is when this graph goes from being positive to negative or negative to positive. You can see at the graph goes like this, where if this is our x-axis, then this is our function, and we have points where this value goes from being negative, which remember, this is referring to the change in x. So our graph would be negative, moving negative, 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 until it switches at this point here to being positive. It's going positive, positive, positive. And then again, we have it happen again over on this side, where it's going from positive, positive, positive to negative, 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 which looks something like positive, 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 negative, negative, negative. So we have a local min here and a local max here. And that refers to, God, this is difficult to do with this graph here. So that refers to these points here and here, which you can see is at 1 and at 5. So we have a local min at 1, and a local max at 5. The thing you need to remember here is that this is not showing us the graph of f, which looks something like this. It's showing us the graph of f prime. This is f prime of x, and based off of that, we can deduce where the positives and negatives switch values. Now we can get this dang graph out of the way, and we can go back to question 19, which question 19 gives us 1 plus 3x squared minus 2x cubed. And we can, what it is asking us to do is to find the local max and minimum values of f using the first and second derivative tests. Now, I'm going to tell you what the first and second derivative tests are, but then I'm only going to use the first derivative test because I think it's a waste of time to do both. The first derivative test is whenever you find the critical points, you mark them on a graph here and here, and then you determine whether these values are positive or negative. If it's going from a positive to a negative, then it's a local max. If it's going from a negative to a positive, it's a local min. That's the first derivative test. The second derivative test has you take the second derivative, naturally, and then it has you determine whether things are critical points, or excuse me, local maxes or local mins, based on whether it's going from concave up, whether it's concave up or concave down. It still requires you to do the first derivative test so you can figure out what your critical points are. So in my mind, it's just a waste of time, and we are not going to do it. So we're going to just do the first derivative test to solve these problems. So we're given 1 plus 3x squared minus 2x cubed. We take the first derivative, which is giving us that f prime of x is equal to 6x minus 6x squared. And then we can set this equal to 0. So we factor out that 6x, which gives us 1 minus x, and we set that equal to 0, which gives us critical points at 0 because of this right here, and at 1 because of this section right here. So those are our critical points. And now we can draw a number line. And we can say we have a 0 here. And let me move this over. We have a 0 here, and a 1 here. Let's plug in a value between 0 and 1. We'll say 1/2 to, and now we can plug in our missing values here. So we say 6 times 100 minus 6 times 100 is going to be equal, or excuse me, 100 squared is going to be a negative number because this number is smaller than this number is. So any values greater than 1 are going to be negative. Then, if we take any values less than 1, we say 6 times negative 100 minus 6 times negative 100. This ends up being a very small number subtracted by a very big number. So, any values less than 0 are going to be negative as well. And then, we need to look for a number between 0 and 1. So let's say 6 times 1/2 minus 6 times 1/2 squared, which gives us 3 minus 6 times 1/4, which is going to be 6 minus 3/2, which ends up being positive. So right here it's positive. So from here we're going negative, negative, negative to positive, positive, positive. Here we're going positive, positive, positive to negative, negative, negative. So at 1, we have a local max, and at 0, we have a local min. It look like this and like that. Now, we can move on to question number 35AB. And that's going to be the last question that we do today. I also have quite a bit of studying to do before this test, and I hope that this could help you guys out as much as possible. This is going to be another graph question. I'm going to pull the graph up right here. This is our graph, 35, and we're going to do AB on this graph. So 35AB asks us to find the intervals where f is increasing and decreasing. And then it also asks us for the values where it has a local max and a local min. So the graph that is given to us is f prime of x. And remember, when f prime of x is positive, f of x is increasing. Here, let me rewrite this. When f prime of x is greater than 0, f of x is increasing. When f prime of x is less than 0, f of x is decreasing. And then, whenever it switches values from positive to negative, that means that we have a local min, or excuse me, a local max. And when it switches values from negative to positive, that means we have a local min. So you can see that this graph does like this sort of thing right here, which means that from here to here, f of x is increasing, which is increasing from 0 to 2. F of x is increasing. And then it becomes positive again here, where it goes from 4 to 6, increasing. And then from 8 to infinity, it is increasing. And then it is decreasing from 2 to 4, and then from 6 to 8, like that. And then we are going to set this up. So we have 0 to 2 is positive, and then 2 to 4 is negative, and then 4 to 6 is positive, and then 6 to 8 is negative, and then 8 to infinity is positive. So from here it goes from positive to negative. So we have a local max at 2, and then it goes negative to positive. So local min at 4, and then again positive to negative, local max at 6, and then negative to positive, local min at 8. So we have local max at 2 and 4, and a local min at 4 and 8. And that's all I'm going to cover for today. I hope that those were helpful. I'm sorry that I didn't get the opportunity to go over exponentials. And also, I'm so sorry, I totally forgot that this tab was right here. This is what this looks like, where we go from the local max of 2 to the local min at 4 to the local max at 6 and the local min at 8. I hope this was helpful. If anybody has any questions, feel free to message me. Good luck on the quiz tomorrow, you guys.